Great.
Yeah, so without further ado, David, on to part two, the needs identification and selection. And just a reminder to the folks in the room that if you have any questions, feel free to throw them in the chat for our Q&A session at the end of part two.
Great, thank you. The next slide, please. So in this section, we'll be looking at the specific analyses that we'll be doing. A high-level overview, of course, of reliability and economic analysis, with a focus on reliability, and then briefly touch on the selection. So just a little bit of history about NERC. It was created after the 1965 major Northeast blackout. NERC develops standards for reliability, both in operations and planning. And these reliability analyses are really the core of transmission planning. They involve multiple perspectives, as I mentioned, a lot of grid phenomena and timescales. So NERC has reliability standards for transmission planning practice specifically, but there are also a lot that are relevant to transmission planning. So this includes facility design ratings and connections, modeling and data and assumptions, and also critical infrastructure protection. We'll focus here on the ones that are relevant to, the ones that are specifically for transmission planning practice. Next slide, please. So there are three standards that NERC has that cover transmission planning practice. TPL1 is the main one. There's a lot there. It can be useful to review it if you're looking for more details. But it basically requires annual assessment of near-term and long-term transmission reliability. It needs to consider both on and off-peak load, and there's also a requirement for contingency studies. So this is really where that translation from the future scenarios into specific power flow cases becomes important. We need them for this NERC TPL1 compliance. And we need to do steady state, transient stability, and short circuit analysis on these. The TPL7 is another one that we won't really touch on. It's for geomagnetic disturbance. And TPL8 is a new one that is still pending approval, which includes this piece about weather sensitivity. So this could be a chance to get into some of those questions about weather and climate at the end of this session. Next slide, please. So I'll just share this for reference, but TPL1 defines a set of 8 different event types that need to be considered under this TPL1 planning. This ranges from a normal system without any contingencies to a variety of different single or joint contingencies. So N-1 means that the system is experiencing the loss of one component. The number of contingencies, if we're looking at joint contingencies happening two at once or more than two, the combinatorics means that the number of contingencies we need to study grows hugely, very quickly. So this kind of puts some bounds on what contingencies need to be analyzed, and the planner has some freedom to define what are credible contingencies, which ones do we need to consider, which ones can we neglect in our planning. Next slide, please. So I mentioned that there are a lot of grid phenomena and timescales involved, and this map just helps illustrate that, I hope. The timescale on the bottom is a log scale going from tenths of a microsecond up to a day, and so that there are phenomena that overlap across this entire timescale, and all of these fit within the realm of reliability studies. So most specific on the top, we have the type of study would be an electromagnetic transient study. This can cover really fast switching events. The next one would be a short circuit study that really focuses on just the specific moment when a short circuit might happen. Next is a slightly broader category, transient stability study, that's really looking from the slower switching dynamics up to any generator dynamics that include both electromagnetics and the mechanical and thermodynamic features. Steady state is really looking at the system in its steady condition, where things aren't changing. We're looking at minutes to hours or up to a day. And then resource adequacy is something we won't touch on too much here, but that's looking at the generator dispatch going into days or even to up to a year. Next slide, please. So first, I want to take a look at steady state analysis. And to do this, I want to highlight three of the main transmission constraints. And these are really what would drive a transmission need that might arise. This is the limitation on power flow. Why would we need to upgrade the transmission system? So thermal limits are one that comes just from the material limitations of our conductors. So as the current increases, there's more heat, the line sags, it might contact vegetation. These limits also depend on ambient temperature and wind, but typically those limits are set very conservatively. The next one is voltage drop. This depends more on the surrounding system conditions, but also on the electrical parameters of the line. So if a long, heavily loaded line has a lot of power flowing through it and it's heavily loaded, then there might be a large voltage drop across it. So this can have larger issues throughout the system. Finally, steady state stability is really driven by the interaction of the line with the rest of the system. It's related to the voltage angle difference across these lines. And the implication would be for generators, so that we could lose stability of some of our generators. So these are all important constraints to consider and plan for. Next slide, please. So here's just an example of how those come into play. And typically this depends on the length of the line. This curve that you see here, it's known as the St. Clair curve, that the black line shows from a circuit perspective, what's the maximum power that can flow on this line. It decreases as we get to longer lengths of the line. So at short lengths, the physics really aren't the limiting factor. It's really this red dotted line, the thermal limit. So for short lines up to maybe 75 or 100 miles, often thermal constraints are the ones that are at play. And I would note that those are entirely arising from an engineering design of the line. So we could upgrade the conductor, we could make a larger conductor or more bundling. That would increase that thermal limit and we could get more power flowing through the line. So that's where reconductoring is something that's an attractive solution, especially for shorter lines. At medium and longer lines, voltage constraints can be an issue. And then at the longest lines, those are typically the ones that we see stability constraints on. And those are distinct from thermal constraints because they really depend more on the operational state of the surrounding system, but also somewhat on the parameters of that line. Next slide, please. So what would this look like in a steady state analysis? We have our power system here. We simulate generation here at 600 megawatts and 580 megawatts of load. Either our AC or our DC power flow model could tell us that there's a capacity violation on this line. that it has maybe it's a thermal overload that can be shown by AC and DC power flow. This would constitute a transmission need. If this shows up in the relevant analyses, we would have to address this violation. Another violation could be voltage. So in this figure at the right, we see that the voltages at all the buses are within this limit of 90 to 110%, except for these two cases where you have under voltage and over voltage. So that would be something that we might need to address in the planning process. And that needs to be done with an AC power flow model. DC power flow can't tell us anything about those violations in voltage. Next slide, please. So I mentioned the differences between DC and AC power flow here. There are a few different software tools. PSSE is used in the Eastern interconnection. PSLF is very similar, used mostly in the Western interconnection. There are a few other examples, both commercial and open source. These are all great tools that have a lot of capabilities in this type of analysis. Terra is one that I would also mention that it's really specialized for contingency studies for these NERC standards, and also calculating transfer limits. It's used by a lot of utilities and planning entities for these purposes. Next slide. The next level of detail is our time scale that we'll look at is transient stability. So this is where the electromechanical nature of power systems come into play. Important values here are the frequency and the voltage. So the plot that you see here shows a disturbance in the system. It could be a fault, a down line, or a sudden addition of load or something along those lines. And you can see the frequency drop. And there are a lot of steps here that if we get below a certain frequency, undesirable things start to happen. There are under frequency load shedding steps that are defined. So if we cross a certain line, then some loads on the system are shed to help bring the system frequency back up. And this is where inertia comes into play. And then as we get farther along, some of the slower responses can happen. But this all happens very quickly within a couple of minutes. If it gets to be very low frequency for a long time, then generators can trip, which is a bad situation because losing generators can make this problem much worse. Voltage has similar concerns about stability. That depends more on reactive power, but also has active power features too. Transient stability is a more complex type of analysis. There are specialized software to look at that. Next slide, please. So a lot of the same softwares like PSSE and PSLF are used for stability studies. There are also open source tools that can do that. Electromagnetic transient studies where we're looking at really detailed switching dynamics can be required when you have a lot of inverter-based resources. This is a much more complex and computationally heavy study. But it's necessary in some cases, especially with a lot of PV or storage or other types of inverter-based resources. So EMTP and PSCAD are great softwares for those studies. Next slide. Short circuits are another one. I won't spend a lot of time on this. We need circuit breakers to protect the system and its components from faults. And the circuit breakers are designed to segment the system to minimize the effects of a fault, but also make sure that it is contained safely. So there's a few different prescribed short circuit studies in the NERC standards. The next slide, please. And why is this important? Because any change to generation and transmission really can impact the characteristics of the short circuit behavior. And this can lead to the need for one or more upgrades to breakers. So it's a very common need for transmission systems. A substation usually has 1 or 1.5 circuit breakers per circuit that enters the substation. And just an example, there was a project in PJM that required a 345 kV circuit breaker upgrade. Just one breaker was a $2.7 million project. So it may seem small, but these transmission breakers, the costs can add up quite quickly. Next slide, please. Many of the same tools can handle short circuit calculations, but there are some more that are more specialized, like grid scale X, which used to be called CAPE, that has really detailed protection setting simulation. Next slide. Now I'll touch briefly on some aspects of economic studies. These have a lot of similarities to what we've already talked about in capacity expansion models. But instead of identifying the generation additions and retirements, we're really focusing on a few different questions. So one question would be, which of the available generator units should be committed to generate the next day? That's known as the unit commitment problem. It's a challenging optimization problem. Then the next question would be, of those units that we have committed, what should each one produce to serve demand at the least cost? So this is the economic dispatch question. And if we add some constraints on reliability under different contingencies that might happen, then that becomes a security constrained economic dispatch. So also a challenging optimization problem. And then these models are both answering the question, how does transmission congestion contribute to the cost of meeting this demand? So shadow prices show how congestion contributes. And then what are the different prices that we see throughout the system on each side of the congested interface? This is the locational marginal price, or LMP. And so this question is really important to answer for these congestion studies. And rather than looking at a single peak hour or an off-peak hour like we do in the reliability assessment, we really need to look at the system as a whole over a whole year of hourly or representative time periods covering a full range of a year or more. So these economic studies really are aimed at providing a comprehensive picture of what the operations would look like under these future scenarios. And from that, we can identify congestion. Next slide, please. So wrapping up this section, we'll get to how do we go from the studies to the needs. So any reliability violation that we have under these NERC criteria, it constitutes a reliability need. And when those needs come up, the planning entity has to address those. There are exceptions allowed if justification and a plan to address them is provided. But for the most part, when these violations come up, they need to be addressed. And I would just add here that the public policy planning process can be separate. That there may be a separate scenario development process that specifically looks at public policy needs, so that can be done together or it can be a separate process. And then, as I mentioned, these persistent sources of congestion are classified as economic needs. Order 890 doesn't require these to be addressed, but they do need to be identified in the process. Next slide, please. So just running through a few of the potential solutions, we could install a new transmission line, either AC or HVDC. We may need substation upgrades, reconductoring, either conventional or advanced conductors, voltage upgrades, series compensation to increase capacity, power flow control to more of an operational option, either with phase shifting transformers or more advanced flexible AC transmission systems. Storage as a transmission asset is another option. And there are also operational solutions like dynamic line rating and transmission switching or topology optimization. And Order 1920 does require an assessment of specific solutions of this list. So next slide, please. So Order 1920 specifically spells out alternative transmission technologies that need to be considered. And that includes advanced conductors, these flexible AC transmission systems for power flow control, dynamic line rating, and transmission switching. So any solution needs to include a comparison with these alternatives and a justification of why one was selected and the other. Next slide, please. So the last slide is just one brief slide on how we get from these needs to solutions. For many ISOs and RTOs, there's a competitive transmission process. So these needs translate to a request for proposals that solicit competitive solutions for these needs. And transmission providers in non-RTO regions have their own processes to manage this. What that process looks like can vary between transmission provider. But there has to be a clearly defined selection criteria in a competitive transmission process. So cost-benefit selection requires the calculation of what those benefits look like. And Order 1920 specifically defines 7 benefits. So if this solution can avoid replacement of transmission, if it can reduce the loss of load probability, improving reliability, economic criteria, production cost savings, reducing the losses of the transmission network, reducing the congestion specifically due to outages, mitigation of extreme weather impacts, and then also specific loss reduction benefits that relate to the need for transmission for generation capacity. So we've discussed a lot of concepts that are very relevant to calculating these benefits. Those would be applied to economic studies that would look at the benefits with each of these different solutions.